Hi, today we're going to talk about covalent bonds, covalent compounds, and electronegativity. Up till now, we have talked only about ionic compounds and why they form. So now we need to talk about the other sort of bonds, and we need to talk about why and how those form differently from ionic bonds. So we talked about why an element like fluorine acquires an electron and gains a negative charge, and we talked about how that negative ion interacts with a positively charged ion to create a molecule with a net zero charge. So why would this not work for all elements? On this periodic table, I have highlighted the element carbon, an element which forms a lot of covalent bonds. So let's think about what it would take in order to get carbon to form an ion. Would it form an anion or a cation? Well, if it formed an anion, it would have to gain a bunch of electrons. How many electrons would it have to gain? It would have to gain 1, 2, 3, 4. 4 electrons, which is a lot of electrons to gain. So maybe it would be easier if it lost electrons instead. Well, let's see, how many would it have to lose? It'd have to lose 1, 2, 3, 4 to get to noble gas electron configuration. So either way you go, it's either going to have to gain or lose a lot of electrons. And the more electrons you have to gain or lose, the higher the energy you have to put in to make it gain or lose those electrons. So carbon and many other atoms in the middle of the periodic table, all those elements still want to attain that noble gas electron configuration, but it is really hard for them to do so by losing or gaining electrons. So what they're going to do instead of losing or gaining electrons is share their electrons with other atoms. And that process of sharing electrons is called covalent bonding. Now, just so you can identify ionic versus what we call molecular compounds, which are compounds formed by covalent bonding. Ionic compounds have a very high melting point, as we talked about. Molecular compounds tend to have a much lower melting point. As I mentioned before, ionic compounds are very brittle, whereas molecular compounds can be very flexible. Another key point is that ionic compounds tend to be very electrically conductive, whereas molecular compounds are not. So when you look at a chemical formula, how would you know if it's a formula for a molecular or an ionic compound? If it's an ionic compound, it's going to consist of one metal and one nonmetal. By contrast, molecular compounds usually consist entirely of nonmetals. There are sometimes when you might have 1 or 2 metals incorporated into a very, very large structure of nonmetals, but generally speaking, the majority, if not all, of the elements in a molecular compound will be nonmetals. So how does covalent bonding work? You're going to have your 2 nuclei, which are positively charged, and you're going to have your electrons located in general between them. And so what's going to happen is both of these positively charged nuclei are going to be attracted to the negatively charged electrons, and that pulls them together. However, I have to say that covalent bonding is a balance of attractive and repulsive forces. So what we have here is we have a graph where on the y-axis we have our potential energy. Remember, that's the energy that could be turned into kinetic energy that will make things move. And on the x-axis we have our internuclear distance, the distance between 2 nuclei that are going to be bonded by covalent bonding. So let's think about what happens if our 2 nuclei are close together, and you can see that the electron clouds are going to overlap here. So you have 2 nuclei close together, both are positively charged. These nuclei are going to have a high potential energy, and that's likely going to turn into kinetic energy as the nuclei move away from each other. Now let's think about the opposite, where we have 2 nuclei that are pretty far apart. So that would be about here on the graph. And you can imagine these also have a relatively high potential energy in that they could move closer to each other. They could be attracted to each other because of the electrons between them. So think about now what's going to happen to our potential energy as the nuclei move closer together. as they move closer together, there's less potential energy that's going to pull them together because A, they've already moved part of the way together, and B, if you move too close together, they're going to repel. So with these two nuclei, there is the possibility for both attractive forces, where the nuclei are going to be pulled together by electrons, and repulsive forces, where the nuclei are going to be pushed apart by their similar charges. And somewhere in between those two extremes, we have the happy medium where the nuclei are as close as they can possibly get without pushing each other apart. So when we talk about covalent bonds, what we're talking about is one pair of shared electrons. Is it possible for atoms to share more than one pair of shared electrons? It is. You can have two shared pairs of electrons, which is a double bond, and you can have three shared pairs of electrons, which is a triple bond. It is not physically possible for atoms to share more than three pairs of electrons, which is something I will explain next chapter. Now, before we go on, I need to talk about a fourth periodic property that we call electronegativity. This periodic property only operates within a molecule where atoms are covalently bonded. And you could think about this as a tug of war. Basically, you have two nuclei, both attracted to the same pair of electrons. And they're both going to be pulling on those electrons. Now, in this little cartoon that I found online, the two kids playing tug of war are equally strong. And so they don't look like either of them is winning. And they could pull back and forth for quite a while. But that's not always true. You can imagine, for example, if one of these kids went home and the other kid's parent took their place, that it would suddenly be a much more unfair contest. And unless the parent let their kid win, which I guess is a possibility, if both were pulling with all their might, the parent would win because the parent is just naturally stronger. And that's how it is with electronegativity. So here's a chart that shows electronegativity data for most of the elements. You will notice that there are a few elements with no data. A lot of them are down here on the bottom. These are man-made elements that don't last more than a fraction of a second. So it's really hard to get them to bond with anything. The rest of them are noble gases, which generally don't bond with anything. Except for krypton and xenon, which is something we will talk about probably next week. So let's talk about trends. Which nuclei are going to pull most strongly on bonding electrons, which are always valence electrons? Well, it's going to be the nuclei that have valence electrons in very low shells. So you can see as you go down the periodic table here, hydrogen 2.2, lithium 0.98, sodium 0.93, potassium 0.82. So it's decreasing as it goes down the periodic table. In terms of going across a period, the farther you go to the right, the higher the effective nuclear charge. And so the more strongly that nucleus will pull on the valence electron. So you expect it to increase as you go across. And if you look at row 2, you can see lithium 0.98, beryllium 1.57, boron 2.04, carbon 2.55, nitrogen 3.04, oxygen 3.44, and fluorine 3.98. So those are, again, increasing as we go left to right. When you have electronegativity differences, you can have what we call a polar bond. And this is a bond in which one of the nuclei is going to pull electrons to it more strongly than the other. We're going to leave it at that for now. As we get into valence bond theory, we're going to talk about what that looks like from a physical perspective. And so for now, we're just going to leave this here. But the nice thing about knowing about electronegativities is that it helps us predict whether we will have a covalent nonpolar bond, a covalent polar bond, or an ionic bond, because these are all based on electronegativity differences. So let's go through and let's look at our electronegativity chart again, and let's look at three pairs of elements that might connect. So the first is a carbon-phosphorus bond. Carbon and phosphorus are here, and you can see their electronegativity values. Carbon is 2.55, phosphorus is 2.19, So our electronegativity difference here is 0.36. We will have a nonpolar covalent bond between these two elements. So if you think about our tug of war analogy, carbon pulls just a little more strongly than phosphorus, but not enough to win the tug of war, if you want to think of it that way. Let's look at another pair of elements, sodium and chlorine. Now this is kind of cheating because we already know what sort of compound this makes, but let's just go through it just for grins. So chlorine is 3.16, sodium is 0.93. We subtract those and we get 2.23. And as you can see, that is an ionic bond. So think again back to our tug of war analogy. What is happening here? You have two atoms in close proximity. One is pulling much more strongly than the other, and it tugs so hard it actually pulls the electron off of sodium and keeps it for itself. Finally, let's look at silicon and oxygen. Oxygen is much more electronegative. It has an electronegativity value of 3.44 minus 1.90 for silicon. That gives us a difference of 1.54. So this is going to be a polar covalent bond in which you're going to be more likely to find electrons near the oxygen than near the silicon. Now that you understand how covalent/molecular compounds are formed, let's talk about how we name them. And mostly we're going to focus on naming binary molecular compounds, where binary means it has two elements. That doesn't mean it has two atoms, it means it just has two elements. So we have a three-step process here. First, we're going to start with the element name of the less electronegative element. That's one of the reasons I had to talk about electronegativity early on. Then we're going to change the name of the more electronegative element to end in "ide." Now, this sounds very much like naming ionic compounds, in that the less electronegative element in an ionic compound is always going to be the cation, and that's what we're going to start with. And then the more electronegative element is going to be the anion, and that always ends in "ide." The difference here is we're going to add prefixes to indicate how many atoms of each element we have in our molecule. So let's do an example. Here is a molecule, P2O5. So we're going to start with the element name of the less electronegative element, and that's going to be phosphorus. So phosphorus is the first word. The next step is to change the name of the more electronegative element to end in "ide." So oxygen is our more electronegative element. So there's phosphorus oxide, which again does sound a bit like an ionic compound. But step 3 is to add prefixes to indicate the numbers of each element. So we have 2 phosphorus, and back to our old prefix table, diphosphorus. And then we have 5 oxygens, so that's going to be technically pentaoxide, but usually if your element name starts with a vowel, you drop the leading A. So that's going to be diphosphorus pentoxide. Now, why would we need prefixes? Well, the thing about covalent compounds is, unlike ionic compounds, you can't predict how many of each element you have. So, for example, if water was just an ionic compound, we would say oxygen has a -2 charge and hydrogen has a +1 charge, so we need 2 hydrogens. And that would be the only way we could write water if it were an ionic compound. But it's not. You see, we can also have H2O2, hydrogen peroxide. Now, those are the common names, water and hydrogen peroxide. They both also have systematic scientific names. So let's write those here. So first we're going to start with the element name of the less electronegative element, which in both cases is hydrogen. So we can write hydrogen for both of those. We then change the name of the more electronegative element, which in this case is oxygen, to end in "ide. So again, we're going to have oxides. And then we're going to add prefixes to indicate the numbers of each element. Now, for hydrogen peroxide, we have dihydrogen dioxide. That's the easy one. They're both 2. for water, we have dihydrogen. And now this technically is monoxide, but because it begins with a vowel, we're going to call it monoxide. Remember that when you have prefixes and you're talking about just one of something, you can also leave off the prefixes. So I would probably call this dihydrogen oxide if I were writing it. So here you can see why we need these prefixes, because we can't rely on charges. So we have two sets of the same elements, but in different numbers. And so we have two systematic names that distinguish between the two compounds. One more, SF6. Again, the element name of the less electronegative element. When we write the symbols for these compounds, we usually write the less electronegative element first. So it's usually the first one in your compound. So that is sulfur in this case. And so there's the first part of our name. The second part, we have to change the name of the more electronegative element, which is fluorine. So this is going to be a sulfur fluoride. And now we're going to add prefixes to indicate the numbers of each element. Now, this is going to be sulfur hexafluoride. And again, we could call it monosulfur hexafluoride, but that's never how you see it. So just a reminder that you can put mono in, but most professional scientists don't put mono in if there's only one. And I just want to emphasize that so you don't get confused when you're looking at chemical bottles. So the majority of the chemicals we interact with on a daily basis are covalent in nature. And it's really important to understand how covalent bonding works, why it works. And we're really going to be doing a deep dive into showing how many atoms of different elements can bond together to make really large molecules. I hope this was helpful, and I look forward to seeing you again soon.